Hello, my name is Kyle Dampier. Today I'm going to be talking about my senior project, Surgery Simulator. So, on the agenda for today, we're going to go have a project walkthrough. Then we're going to do it how I plan to test my project, some of the current problems I'm facing, and then the responsibilities that I have coming forward to actually finish this project. So now let's go right into the project a walkthrough. Um, so processing medical imaging data is crucial. There are current solutions to project the 3D images that we get onto 2D screens, but that requires the user to translate the series of 2D images into a 3D visualization, which can be time consuming and hard to learn. Um, Also, labeling structures like livers and bones can be time consuming for the doctor, and a surgeon's time is extremely valuable. Lastly, so the basic idea of this project is to combine a solution for both of these problems: a very intuitive 3D visualization and a way to structure the livers and bones without having like a time-consuming going through and picking which pixels are which. So this is what the current DICOM scan import screen looks like on the project. So I'm actually going in on a project that's in progress. I came in to help. So yeah, this restructured voxel cloud in VR. So this is what the voxel cloud would look like in VR. You can see that there's different colors for different labels. So the pipeline example. So this is what the pipeline kind of looks like for a doctor, where you have the scan, the VR model. And from the VR model, you can go in and change the labels, and then you can say like where the veins are and stuff. And then once you have all the veins, you can go in and simulate. The step that I'm trying to make less time consuming for the doctor is the step between the scans and the VR model. So here's some of my results. So as you can see, for bone, this is quite a good result. And it has different colors, but that's just because I don't do all the labels, and I'll talk about that later. And here's one of the problems. So as you can see, it's not that bad of a label, but it's flipped. I don't know what went wrong in my code somewhere, but yeah, I'm gonna have to figure out where that problem is, but that is one of the issues that I'm currently facing. Now, how I plan to test the project. So there are two main ways to basically compare model performance when it comes to these types of tasks. The first kind is dice similarity coefficient. This evaluates the performance of the reproducibility of manual segmentations and the spatial overlap accuracy. So basically, this just is basically like a harmonic mean of how many of the labels you got right for the correct label and the wrong labels for the wrong label. Typically, this is used to say how reproducible and sort of accurate the actual segmentation is, and it performs cross-validation on every pixel. So basically, it's like doing a cross-validation on every pixel, so it's very computationally complex. And this can also be combined with a technique called K-fold, which, if you want, I can't go into the details on that. The mean intersection over union, or the MIOU, takes into account the region common to both and computes the percentage similarity. So it's basically if it's a right label, then it counts it, and then it divides it by the total amount of things that it was supposed to have in that label. This is effective on the segmentation of multiple classes. So this is kind of a visual of what mean intersection over union actually looks like. So for a comparison, these are visual comparisons of the dice similarity coefficient and the mean intersection over union. You can see that the dice similarity coefficient looks kind of similar to what we call in math called a harmonic mean. And yeah. I also need to check quadrants. So when you get a scan, it's not always the same XYZ coordinates. So I have to be able to go in the header and figure out which quadrant is which when I send it over to Furby, because if we have labels and we have the scan, we need to basically overlap them together, and when we overlap them together, they can't be on different coordinate systems. So here are some of the issues that I'm facing outside of those. The inference time for my model is very slow. As you can see, it takes about 185 seconds to sort of infer an entire scan. And most of the speed improvements are actually not in the model itself, but the actual post-processing. Since I use PyTorch and PyTorch uses the GPU, I need to create a better solution for the post-processing, which essentially I can just go in here and each voxel essentially has a class that it predicts, and then I basically take the argmax of that class, and then if the confidence of the class that it thinks is the max is greater than 5, it chooses that class. Otherwise, it chooses 0. Another issue I'm facing are large file sizes. Sending data between Unity and Python is really challenging when a lot of the files are over 200 megabytes in size. As you can see by my listed directory, that it's about an average of 200 megabytes per scan. That could be rough because if you're a doctor and you don't have enough memory on your computer, or you don't have enough storage on your computer, then you will face problems that, when you're a doctor, facing technical problems is not very good at all. So more about our data set. So right now I've just been using the ctorg data set, where they're stored in an nii.gz format, and they contain the labels background, liver, bladder, lungs, kidneys, bone, and brain. This data set has 140 labeled CT scans, and it was annotated in the years 2018, 2019. And then this is where I got the data. So incomplete data. So my data that I've been using is kind of incomplete. So as you can see, there's a lot of different numbers of slices. So this is essentially the distribution of slices for all of the samples. And you can see that it goes all the way up to like 1,000 to like 100 slices. So it's hard. So when you make a model, you have to have a constant matrix, because that model expects a certain size. But if there's if the actual scans have like a lot more slices than the ones before it, then we have to choose which data to actually label, which can be very complicated. The label percentage. So this is the percentage labels with the standard error. So the standard error is in the black. So as you can see, 0, nothing is pretty good for a standard error. 1 and 2 seem fine. 3 seems fine. But as you can see, like when you get to the lower percentages, the standard error almost becomes the point where it's not even like we don't know for sure that all the scans are going to have that label or enough labels for it to actually matter. So I went ahead and I did a distribution of each of the label percentages in the data set. So for background, you can see that this distribution, most of the labels are background. So here's the liver distribution. This one's not that bad. Here's the bladder distribution. You can see a lot of them have 0 or close to 0 labeled bladder, which is one of the things that we actually want. So here's lung. Lung is actually very good. A lot of the data set has lungs to predict. Kidney is probably one of the least prominent labels in the data set, but as you can see, some of them have a bunch of kidneys, but most of them don't even have kidney at all. Bone distribution. Bone is another one of the ones that we're really looking for, and bone has a very good distribution. So my responsibilities. So my responsibilities as of now are still to create the Unity Python lifecycle, where Unity starts Python and Python creates a connection, and then Python waits until Unity sends them a file. It basically allows the metadata and file path. It basically sends the metadata and file path of what she wants, and then I do all the processing in Python because it's a lot easier and more user-friendly or programmer-friendly, and then I just output to her a .mpy file that she can use in her own in the VR system. So another one of my responsibilities is data cleaning. So I have a plan for this. So I talked to my advisor, and she told me to focus on 3 objects: bone, bladder, and muscle. We don't have muscle, but bone and bladder are the 2 that I'm going to really focus on and make sure that all the data that I have actually has those 2 labels in it. So basically, I'm going to filter the samples with a high percentage of those classes, and then train only on those required classes. This basically makes it so when I create the output of voxels that each voxel has their own class, instead of predicting 5 classes, I'm only predicting 2, which makes the model a lot more efficient. Then I need to identify and crop for a consistent amount of slices. So essentially, I just need to figure out what's the area we need for our use case, and basically crop only that area and create a consistent amount of slices, so I can create a better model from that. Thank you.